So the moral of the story might be solving polynomial equations is hard. Anybody taking an algebra class in high school will tell you that, of course, that's the case, right? Even solving a quadratic equation is not always a picnic, right? That just because your quadratic equation, for example, looks really simple, its coefficients are, I don't know, 1, 0, and positive 1. What could be more simple than that? That even a simple quadratic equation over the integers, you might have to go all the way up to a very complex number system, no pun intended, or maybe pun intended, right, because you need the complex numbers, in order to find the roots of that polynomial. So solving polynomials is no easy task. We may need to go to a much bigger number system than the number system out of which our polynomial is built in order to find its solutions. So what we want to do is to begin to poke at the boundaries of that next, and think about what does the process of solving polynomial equations look like, both in some specific examples and maybe pushing towards some more general cases. And then by the time we get to the next video, we'll see how group theory can actually help us to do this process in a little bit more systematic and enlightening way by kind of changing our perspective on how we do what we do in algebra. So solving polynomial equations is hard, but we do have some techniques that will permit us to reduce polynomial equations to equations that are simpler. For instance, one of the things you spend a whole lot of time doing in your high school algebra class is factoring. And factoring is really an art more than it's a science. But the good part about factoring is that if I can factor a polynomial into a product of two simpler polynomials, for instance of lower degree, then the zero factor property lets me split those two apart, and I can solve those simpler equations, find the roots of the simpler equations, in order to find the roots of the big equation. So t squared minus t plus 2. So here's a polynomial over the integers. I can factor this polynomial, t plus 1, t minus 2, and note that when I factored this, my 1 and my negative 2 that I built these factors out of are also integers, which is great. Then the zero factor property is going to let me split them apart. Again, this is the high school algebra dream. High school algebra likes it this way, that when you factor a polynomial in high school algebra, if you can't get it to work with integers in the factors, then generally you just say that you can't get it to work, right? You say, if you can't factor it and find the two integers that work, then you're just going to not factor. We'll see this semester that we can actually do a little better than that. But once we have it factored, the zero factor property lets me break apart each factor and set it equal to 0, and then solve each of those much simpler equations for t. And it gives me my two roots, t equals negative 1 and t equals 2. And the zero factor property seems like an obvious thing in the real number system, because in the real number system, the product of two non-zero real numbers is always non-zero. But this is a property that we can't always take for granted. That the zero factor property is not a trivial thing. It doesn't always exist in a given number system if that number system is not the reals. For instance, if we have a system where our elements are not numbers but 2 by 2 matrices, here's an example of a pair of 2 by 2 matrices which are not the zero matrix, but if I multiply them together, I do get the zero matrix. So the product of two non-zero 2 by 2 matrices might indeed be a zero 2 by 2 matrix. So the zero factor property is not a slam dunk, but it does hold in the, we'll call it a field of real numbers. So the zero factor property is nice when we can use it, which is most of the time. Just be aware that it's not a general universal principle that holds in any system of arithmetic that we can do more abstractly. So if we factor and leverage the zero factor property, we can generally solve a polynomial equation. But here's the different tack that we want to take on how to reduce a difficult polynomial equation to some set of simpler polynomial equations. And the idea is this. Instead of solving the original polynomial, let's try to find other polynomials that have the same solutions. And ideally, what we'd like is to be able to have some process, some deterministic process that will allow us to construct those other polynomial equations that are simpler with only some knowledge of what the coefficients of our original polynomial is. What in the world am I talking about? Well, let's illustrate this with an example. So t to the fourth minus 256. Here's a polynomial of degree 4 over the integers. We could factor this just using the techniques of high school algebra into t squared minus 16 times t squared plus 16. And once we've done that, the zero factor property will help us to find the roots of our original polynomial p. And some of those roots of p will be roots of this first factor, so some of them will satisfy t squared minus 16 equals 0. And the others are going to be roots of the second factor. They'll satisfy t squared plus 16 is equal to 0. The good part about each of these two pieces is that each of these two pieces is also again, a polynomial over the integers, right? The coefficients of t squared plus or minus 16 are still integer coefficients. But the bad news is that that's not always going to be the case in general, right? We might not always be able to factor one of these polynomials over the integers. That if I try to break it apart and factor it, that I might get irrational numbers or even worse, complex numbers as the coefficients in these polynomials, the polynomial pieces. So is there a way to construct maybe a different set of equations with just some knowledge of the coefficients of our polynomial? So can we find simpler polynomials with integer coefficients that also have the same roots, the same solutions as the polynomial p, and hopefully be able to use the coefficients of p to find such equations? So here are some examples. Let's again take this same polynomial and ask the question, what other polynomial equations might take the roots of p and unite them together? In other words, not just a polynomial equation in a single variable that one of the roots of p might satisfy, but maybe polynomial equations in several variables that if I put several of the roots of p into will be satisfied. So what polynomial equations can tie together one or more of the roots of p? So if I factor p again, and I factor those factors, and I have to go to the complex numbers in order to do that, but I can actually find out what the four roots of this p are just by factoring completely and then solving using the zero factor property. I get four roots, plus and minus 4, and then plus or minus 4i, where I is the square root of -1. Let's call those roots by names. Let's give them the names alpha, beta, gamma, delta. So there are the four roots of my polynomial p. Notice that the first pair, alpha and beta, are opposites of one another, plus and minus 4. So those two are related one to another. So they satisfy a very simple polynomial equation in two variables, namely alpha plus beta is equal to 0. So the fact that those two roots come in a pair of opposites is important. It means that those two roots are not so different as they might otherwise be. Likewise for the second pair, gamma and delta, plus and minus 4i. Those are also opposites, and so they satisfy the simple polynomial equation in two variables, gamma plus delta is equal to 0. So here are a couple of equations that the roots of p satisfy, and these equations are polynomials in two variables, but they're still polynomials over the integers. 1 alpha plus 1 beta is equal to 0, and so forth. So this is an expression that the roots of p, this particular p, come in two pairs of opposites. Plus minus 4 are alpha and beta, plus minus 4i are gamma and delta. But we can get fancier. We can take these two equations that are satisfied by alpha and beta and gamma and delta separately and add them together to get an equation that relates all four of the roots together. Alpha plus beta plus gamma plus delta is equal to 0. So here's a polynomial equation in four variables that's satisfied by the four roots of p. We can get fancier too. For instance, alpha squared minus 16 is equal to 0 is satisfied by, well, one of the roots at least of this polynomial. It's satisfied by alpha, -4. Notice that it's also satisfied by beta, but it's not satisfied by gamma or delta. So putting alpha is a deliberate choice in this equation, because it doesn't work if I put just any root in there, but it does work for alpha. Likewise, if I take alpha and beta and I multiply them, I get -16. If I multiply gamma by delta, I get positive 16. So I can build what looks like a quadratic polynomial equation with all four of these variables if I, say, add these two products together and get 0. So alpha beta plus gamma delta is equal to 0 is another polynomial equation in these four roots that is satisfied by alpha beta gamma delta, the roots of p. If I multiply those products together instead of add them, so if I multiply all four, alpha beta gamma delta, I get -256. Therefore, the roots here satisfy alpha, beta, gamma, delta plus 256 equals 0. We could keep going. Right? There's a whole bunch of choices, lots of options on different polynomial equations that are solved by the roots of p. But when we constructed these, we knew what the roots were. Is there a way to construct these equations without knowing what the roots of p are? So we might look for a clue in the fact that one of these equations has a 256 in it that we didn't have to look very hard to find in our original equation. It was one of our original coefficients. So the name of the game is to figure out if we can construct equations that are solved by the roots of p without knowing what those roots of p actually are. So what we need to do next is think about how this process becomes more systematic. How can we construct polynomial equations with integer coefficients that are satisfied by the roots of a polynomial without knowing what the roots of that polynomial are. And the key is going to come in observations like the one we made a couple of slides ago, namely that for the polynomial we looked at, we had a pair of roots, plus and minus 4, that were kind of together. They were very similar one to another. We had another pair, plus and minus 4i, that were together. They were very similar one to another. So by observing similarities in the patterns of the roots, maybe we can learn something about what the roots of that polynomial actually are. And we're going to see how group theory helps us to do that in the next video.